Swayam Prabha. Digital India. Educated India.
Hello, welcome to yet another session of our NPTEL on Nonlinear and Adaptive Control. I am Shrikant Sukumar from Systems and Control, IIT Bombay. I warmly welcome you to the week number 11 of our course, and I really hope that we've had a very good journey together. We have already learned several methods, several algorithms that will help design robust adaptive nonlinear laws that drive autonomous systems such as the SpaceX satellite that you see in our background. With this sort of an introduction, I want to talk a little bit, go back a little bit to what we were doing in the previous week. So we actually started off talking about what is robustness and what is the need for robustness in adaptive control, and we got a pretty good idea that in the presence of disturbance, a disturbance that would not really trouble non-adaptive laws, uh, what happens in adaptive control setting is that this disturbance can result in our parameters going unbounded and subsequently the control also becoming unbounded in order to maintain a nice bound on the tracking error. This was, of course, rather undesirable, and we first talked about tackling this using the parameter projection method, right? In which we assumed some prior knowledge of bounds on the parameter, and with this prior knowledge of bounds on the parameter, we design adaptive laws using projection functions like tanh hyperbolic functions, which will allow you to keep the parameter values within this given bounds. All right. Now, one of the, of course, we did the stability analysis and we figured out some nice properties for such projection based adaptive control laws. One of the sort of issues, or well, I mean, one of the sort of concerns that may be raised on in such solutions is that you require knowledge of the bound on parameters, though it's a very reasonable assumption. But if you do not have such a knowledge, then there also exist solutions. They're called the sigma modification and the epsilon modification. The basic idea being that the standard adapt certainty equivalence adaptive law is augmented with a damping term, which was not present in the typical certainty equivalence law, right? And what this damping term does is it creates a residual set in both A tilde, that is the parameter error, and the tracking error. Now, one of the issues, well, couple of issues. One of the issues is that even if the disturbance is zero, we only get bounded performance with such kind of analysis, right? Which may more or less be okay for most practicing engineers, but may not be okay with some theoreticians, right? They would say that if there's no external disturbance, why am I still getting, sort of poorer performance, or not ideal performance, right? The other issue is that because of the structure of a hat dot, when E goes to zero, that is, E becomes very close to zero, you see that this term starts to dominate significantly, and whatever parameter value has been learned, A hat, suppose A hat has gotten rather close to the true value A, but that gets unlearned because this term will push every A hat to zero, right? So you unlearn the true parameter value, and this can, of course, cause a deterioration of the tracking error performance also. And this is where the epsilon modification came in, where instead of a constant gain sigma, the gain is now in absolute value of the error itself, Therefore, when the error goes to 0, then this term also goes to 0, and whatever parameter value you've learned until that point remain as it is, so there is no change. All right, so that's sort of what you would the best you can do in some sense, right? Again, of course, this also suffers from the same issue. In fact, the residual set expressions are exactly same as before. So even in the absence of the disturbance, we will get only uniform ultimate boundedness. All right. But in any case, these were rather useful solutions, I hope. Yeah, I mean, for realistic applications, these are rather useful solutions, and either projection or sigma epsilon modification are more than sufficient to impart robustness to your adaptive control against unmodeled disturbances or unknown disturbances, right? So as long as the disturbances are bounded, you are good to go. Now, we have by this time seen covered more or less large breadth of the adaptive control. Of course, it's like any other field, it's huge, and always more to learn, more to do, and more remains to be taught. But of course, we can't expect to do everything. But we have uh, covered a very large portion of adaptive control, and most importantly, all of you have been enabled to do your own design, yeah, own adaptive law designs, as you go along. Yeah. Now, what we want to do henceforth is more modern ideas, or ideas that are becoming more popular now in adaptive control. Uh, One of the first, uh, sort of topics that we want to do, and this is where we will start today, is basically initial excitation based adaptive control. Now, as you can see, this is not too far from, pretty recent work. And so one of the sort of issues in adaptive control is parameter convergence, right? Or parameter learning, as you would say in modern terminology, right? Now, this parameter learning requires uh, persistence of excitation. This is well known, right? Now, persistence of excitation, as the word says, is persistent, right? So it has to exist for all time for you to be able to do good parameter identification. And this may not always be possible, right? This may not, especially when you are sort of close to being done tracking, you want to move on and probably do another tracking problem. So you may not have enough persistence, yeah, in your signals for you to have learned the parameter value perfectly. So a lot of research went into relaxing this persistence condition, right? And this is what is called initial. Well, this one of these methods is called initial excitation-based adaptive control, and the authors here are from IIT Delhi, so very local. You're being vocal for local, yeah. But very interesting bit of work, interesting sequence of work on relaxing persistence excitation, right? So this is sort of a reference point. So what we'll do is we will look at a simple version of what they propose. Of course, they are proposing all of this for, as you can see, Euler-Lagrange system, which is essentially the standard model for robot systems. So we will of course look at slightly simpler, version of things for classroom illustration purposes. You can very easily extend this to, once you understand this, you can very easily extend this to the robot problem or any other, control problem you might have. All right. So let's begin. This is where we start our this week's lectures. Right, lecture 11.1. Right. So as usual, let's continue with a single integrator setting. Right? So I have a single integrator model. This could have been nonlinear or linear. It doesn't matter. Nothing much changes there. It's okay. As long as you have this kind of a linear parameterization, A. So A is unknown. There is a control. I mean, A is, more often than not, A would be positive because otherwise this is stable and nothing much to do. And the typical objective is to track a reference signal R. And so as always, we construct an error signal x minus r. But before we go on to do any control design, we start to look at the parameter design. Okay, so this is going to be similar to the non-certainty equivalence method that we saw in projection and algorithm, the projection-based adaptive control algorithm. And so this also has a similar feel in the sense that the parameter update, yeah, is sort of uh, done separately from the Lyapunov analysis. Okay, and we'll of course talk about it a little bit more later on. So what we do is we want to express our system, any system for that matter, in this case a single integrator, but we want to express any system in a standard uh, regressor parameter form. And what is the standard regressor parameter form? We want to write our dynamical system as y theta equal to u. Yeah. If there's an unknown connected to u, of course, that's a separate problem that can be dealt with also. But right now we only deal with the problem where there is the control gain is not unknown. In fact, it's identity. So we write the system as y theta equal to u. This is what we do for all dynamical systems, not just for the single integrator. So in order to do this for the single integrator, you notice that I have constructed a regressor and a theta. Now the interesting thing to see here is that because I want to write it as y theta equal to u, I have no choice but to augment the a with a 1 in theta. Yeah, otherwise this dynamics and this will not match. Yeah. This I have to do, and this is common in this initial excitation based adaptive control. We have to do this, that we have to augment our parameter a with a 1. So there is a over parameterization. We are trying to identify something that we already know. Right? 1 is not unknown, but we will try to identify it. Yeah. So already you see one, if you may, one disadvantage, if you may, of this method. All right. So you have y theta equal to u. Okay. So where y is the regressor, which is basically x dot and x, and theta is 1 and a, and u is of course retained as such. Yeah. So that's what we mentioned here. There's over parameterization as 1 in theta is not unknown. All right. Right. Now we start with the process of defining filters. Again, this should be reminiscent of non-CE projected projection based adaptive loss. Yeah, this is should be reminiscent of non-CE projection based adaptive loss. In fact, why is it so reminiscent? Because most of these authors have followed an earlier author's work. Yeah, so Slotine had sort of proposed this idea in 80s. Yeah, you can look up this reference. Yeah, I mean you can find this reference. So therefore, a lot of authors are using similar ideas. So even the projection based adaptive control, the non-CE version, was by Akella, and they also are motivated, of course, by this Slotine's work in the 80s. Yeah, that's the idea. Now, what's the idea again? In there also, if you remember, in this equation, you essentially filtered everything that was known to you. All known quantities got filtered, right? So what is known, the regressor is known and the control is known. So both of these are passed through a filter, a low pass filter, if you may, with some bandwidth sigma, which is positive, of course. And the additional thing here is you ask for you require zero initial conditions, right? So in our earlier sort of result, the initial conditions were not specified, but here we are specifying the initial condition, right, to be zero. These are again filters that are implemented in theory. I mean, in the sense that they're implemented on a computer. They're not real data coming from any real dynamical system, so we don't have to worry about the initial conditions not being exactly zero. So once we have assumed this sort of a filter structure, apologize. right? This sort of a filter structure and some initial conditions, I can actually solve for this. Yeah, so we are sort of trying to verify the implementability of this filter structure, filter. All right. So we just integrate this using standard variation of parameters integration. So the solution of this for zero initial condition is just this e to the power minus sigma t integral from 0 to t e to the power sigma tau y tau d tau. All right. So that's it. This is the solution. And now I can substitute for y, which is just x dot and minus x. Right. So this is actually, if you notice in this case, y is actually in, right. It's a 2 row vector of size 2. All right. So now if you look at this first term here, there's a little bit of a problem. Typically in a state space system, x dot is not measured. Right? You measure the states, but not the derivatives of the states. So this is the typical assumption in a state space system. All right. So, so the question is, can we still implement this kind of a filter? And the answer is yes. Yeah. Otherwise, I'm sorry for that. Otherwise, the authors would not have proposed it, I guess. Right. So if you look at this term, we want to see how to deal with this particular term. This term is of course implemented, right? No problem. Right? Because x is available, so all I need to do is integrate this or whatever. I mean, or just solve this differential equation with this x piece, no problem, right? So that's what we do. We look at the first piece of the integral here, which is this guy. Yeah, not implementable because x dot is typically not available for measurement. This is very standard assumption in state space design. Okay, all right. Now, how do we resolve this? We just do integration by parts on this guy. So what is integration of parts by parts of this guy? It is just whatever, the scaling remains as it is. And then you have first times integral of second, and then minus integral of differential of first times integral of second. All right. We're just applying the integral by parts formula. Okay. And now you see something nice has happened. What is this something nice? You see that this thing is now implementable. Right? It is, I mean, x is known. Anyway, this is implementable. We'll anyway look at it further. And this quantity can be evaluated. So this, if I evaluate this whole thing right here, you get this. You get x at time t minus e to the power minus sigma t x0 minus sigma e minus sigma t 0 to t e to the power sigma tau h tau dz. Right. So nice. Everything looks like an integral or integrable term. Everything looks like it's using measurements that are available. Right. So that's good. In fact, if you look at this particular quantity, this is actually the solution of this system with zero initial conditions. All right. Very standard, very easy to verify, right? Excellent. So that's what we do. We just write it in terms of this new variable h, just for ease of notation. Otherwise, you can directly use this also, no problem. So therefore, what do we have? We have yf is actually equal to e to the power minus sigma t e to the power sigma tau x tau d tau. This is the second term, by the way. This is just the second term here, right? I hope I got the sign correct. I think this should be the second term is a negative term. So I think this should be a negative sign, I believe. So this is minus e to the power minus sigma tau 0 to t e to the power sigma tau x tau d tau. And then you have xt from here, right? Minus e to the power minus sigma t x0 from here, minus sigma h from here. And if you now look at this term also, this is also in fact equal to h. And this is also equal to h in this particular case. So this actually becomes minus sigma plus 1 h plus xt minus e to the power minus sigma t x0, right? So the important thing to remember is that h is implementable because x is known. Therefore, yf is also implementable. All right, pretty straightforward. Okay, because x is known and h is known. So in fact, I can be more precise here and say that this is actually h evaluated at t, right? H evaluated at t. Okay, great. So we have essentially constructed a filter, yeah, an unusual filter because we also have the derivative of the states in here that is being filtered. Right? But the important thing to remember is that this filter is implemented. Excellent, great. Because you don't want to design something that's not implemented, correct? Right. Now let's look at some properties of these filtered variables, right? If you remember, even in the projection based adaptive control design also, we sort of tried to relate the or write the dynamics in terms of the filtered variables also, right? So we are sort of doing something similar, not exactly the same, but something similar. So if you look at this yf dot, it is just minus sigma yf plus a y, right? So if I multiply by theta on both sides, I get this. And notice that y times theta equals to u from our regressor parameter form. So I have just substituted here. And now, because theta is a constant, this is possible only because theta is a constant. So if I take the derivative, if I take y of theta as a variable and I take the derivative, I get exactly the left hand side. And on the right hand side, I have minus sigma again times y of theta plus u. And y of theta at 0 is 0 because yf at 0 is 0. Right? So if you compare it with the UF equation, I will write it here for your reference. If you compare it with the UF equation, what do you note? You note that these two equations are exactly the same. Right? These two are exactly the same equations with the same initial conditions, right? So it's just different notation. So what does it mean? It means UF is equal to YF theta, right? So this is very similar to what we did in projection based adaptive control, right? Even there we found an equation in terms of the filtered variables, and that's exactly what we are doing here too, right? Because the original equation was y theta equals to u in the regressor parameter form, and we notice that just like in the projection based adaptive control method, the filtered equation also has a very similar structure, just that the y is replaced by yf and the u is replaced by uf. All right, and this is of course a very important property that gets used subsequently. All right, so remember, so that's what I would say. Uh, Similar to original y theta equal to u, as in projection based adaptive control. Yeah, again, not a surprise. Most of us researchers are always motivated by some past work, and multiple researchers could be motivated by one seminal piece of past work. So this work by Slotkin in the 80s, who also proposed having filters, is of course something that a lot of people refer to. Yeah, and so of course you have very similar feel to this as opposed to when you compare with projection based adaptive control, right? Now one thing we know is that the performance of this system does improve by adding filters. How do we know this? Of course we didn't do anything, Slotkin did. So they also showed that the performance improves. And also we did in the projection based adaptive control, you remember that because of this filtered variables, you got some kind of a attractive set here. Yeah, you see, you got an attractive invariant set, yeah, which is omega equal to 0. Yeah, we got an omega equal to 0, which was an attractive invariant set. So this is sort of what Slotine also proved, right? And that's what you get when you have a filtered, like a filter system. You can expect to get this kind of convergence to some attractive set kind of behavior, which improves the performance of the adaptive control. However, this does not allow you to get rid of persistence. Yeah, I mean, even here, uh, in this system, if you notice, all you are guaranteed to get is that omega goes to 0. And what was omega? Omega was some complicated function of the unknown. Yeah. So this quantity going to 0 does not necessarily mean the parameters are converged. Right? It's just that this quantity is going to 0 and you need some kind of persistence condition on probably xf or something to get parameter convergence. All right. So that's the important thing to remember, that persistence condition is not uh, cannot be done away with just because you filtered it. And this is the sort of lesson that was well understood. And in order to uh, relax the persistence condition, these authors, that is Shubhendu and Shayan and Indrakar from IIT Delhi, they proposed the introduction of a second layer filter. Right, so this is the innovation. Okay, the addition of a second layer filter. So earlier it was just filtering y, now they filter yf. How? It has a very specific structure. Yif now is the new variable. Yif dot is just minus yf transpose yf, again with 0 initial condition. And uif dot is just yf transpose uf with 0 initial condition. Okay. So this is the second layer filter, which will in fact help us to get rid of the uh, persistence of excitation requirement. All right, excellent. So what did we look at today? We started talking about uh, one particular method which helps relax persistence of excitation condition, which may be a rather steep demand on a dynamical system, because having excitation uh, infinitely is not a very feasible requirement. Therefore, in order to relax such a requirement, there is some recent work which which relies on the filter ideas that we've already seen in projection based adaptive control. The only thing is, instead of a one layer filter that you have in the projection based adaptive controller, which is again motivated by Slotine's work in the 80s, here we have a two layer adaptive filter. Okay, and we will see how this will result in construction of an adaptive law without without requiring a Lyapunov function. And subsequently we'll also see how it relaxes the requirement for persistent excitation. Right, so that's really the idea. And we'll see how this helps improve the system performance. Right, so we are looking at a single integrator system, of course, to keep things simple. But once we understand that once we can follow this, we can very well follow the work on double integrators, and we can also work with Euler-Lagrange systems, spacecraft dynamics, and so on. Things like, again, autonomous systems, such as what you see in the background here. All right, great. So I'll see you again in the next session. Thank you.